Hello, everyone. Welcome to the Casual Causal Talk, episode 6. Today, we have with us Dr. Ryan Batten. He's an interesting figure. He posts a lot of content on LinkedIn, making causal inference very easy to digest for everybody. He's interestingly a civil engineer who has transitioned to epidemiology, and now he works with a company called Phastar. Dr. Ryan, welcome to the show. How are you today?
Thanks for having me. Good, thanks. How are you? Thank you for having me today.
Great. I'm doing good. The very first question that I have for you is, how did a civil engineer end up, studying epidemiology, and basically what prompted this transition?
Yeah, so thanks. It's a very fair question. So I first did a bachelor's degree in civil engineering at Memorial University in Newfoundland. My real passion was math and physics. So after high school, engineering seemed like kind of the logical next step. But when I finished in 2016, the job market wasn't fantastic, and I wasn't sold on if that was necessarily the career path for me. So I talked to a family friend who's now my supervisor, and he told me about this field, epidemiology. So first, I thought it was naively, I thought it was about like biology, chemistry, which my background's not, and quickly found out there's more about study design, statistics. So I first started with doing a couple of courses that led to doing a master's degree, and then led into my PhD, which I'm hoping to finish by the end of this year or early next year.
Nice. So we can soon call you Dr. Ryan Batten. Maybe we
Very
can
soon.
already do so.
Soon. Yeah, exactly. Yeah. So I've passed my candidate exam, so the comprehensive exam, but hopefully we'll be officially finished early next year, so January.
Great. I think one thing that civil engineering has in common with biostatistics is the mission criticalness or the rigor. I mean, you can't afford to goof up in civil engineering. Like if you do so, buildings could collapse on you. And similarly for biostatistics, you can't, afford to make an error because lives could be lost. There is an interesting book, a very ancient book. It's called the Hammurabi's Code, which says that if you are a civil engineer, you construct a building and the owner who resides dies because the roof collapses, you will be put to death. So
Mhm.
there is so much skin in the game when it comes to civil engineering. I'm pretty sure with respect to biostatistics also it's very similar. uh, and one interesting thing that I saw on your profile is that does coffee cause happiness? I have a
Mhm.
coffee with me right now. I'm a bit
I
happy.
do. Yeah. Yeah.
Yeah. So, this is a reference to, the Wyatt's 5 levels of experiments. This is a question that I pose to everyone. If you were to explain causality to, a grandma, to a college fresher, and a fellow causal expert, how would you go about it? I mean, you can take the example of, the coffee causes happiness itself. Yeah.
Absolutely, yeah. And I'm glad you asked because I also have a copy with me as well. So at a high level, it would be basically just that. Does coffee cause happiness? And try to have people think a little bit about what exactly does that mean? What are some things we need to consider? Is that the same for everyone? And that kind of leads into the college refresher of thinking through what to better define the question of what do we mean. So causal, does coffee cause happiness? I would say yes for me. That's my individual effect. And we're talking about on average. So if we give everybody coffee, would they be happy? Sometimes that causes some frustration between results from a study, from like a clinical trial, and to somebody, a patient, because they can't understand why a specific drug hasn't worked for them. But it doesn't work necessarily for each person. It's more on average. And then to a fellow expert, I asked about how we're going to define this. Do we mean iced coffee? Do we mean hot coffee? Do we mean stale coffee? I don't think stale coffee would cause happiness. So we need to like clearly define that. We'd probably draw a DAG, and have some criticisms of it, discuss some assumptions, and then different methods, what we'd like to use, what would be most appropriate. Um, that's kind of I don't know if that makes sense, but that's kind of the way I would look at it.
No, it does, definitely. Yeah, thanks for those explanations. And generally speaking, there are two ways to establish causality. the good old randomized control trials, and then you have the observational data, you have your quasi-causal methods, arising out of those observational data. Uh, why is it that RCTs are considered gold standard? Are they really gold standard, first of all?
Yes, that's a great question. And I think yes would be the answer to that, which is funny considering most of my work is not with RCTs. But for causal inference, there's assumptions that need to be met. How easy, quote unquote, it is to meet these assumptions depends on the method. So, for example, for an RCT, it's easier to meet the assumption of exchangeability because you're randomizing patients. So both patients, you're breaking that the arrow in a DAG between a confounder and the treatment variable or the exposure. Whereas when you're using a model, you're assuming that you've captured all of it correctly, yet there's no unmeasured confounders. So it really boils down to what assumptions and how easy is it to meet those. That's not to say that every RCT should be viewed as a gold standard. In my opinion, a well-conducted RCT is the gold standard, but there's also caveats to that. An RCT is a controlled environment. You do have people who are participating in it that may be different. So one example is medication adherence. In an RCT, you can account for that, and there's trials that do. But in the real world, somebody might not, or there might be external factors that weren't accounted for, patients that are potentially sicker. So RCTs are great for asking the question, does this treatment work in this group of people? But that's not without caveats. And sometimes I think observational studies get a bad rap because they're not necessarily worse, they're just different.
Yeah, that was going to be my second question. In relation to, let's say, RCTs, the observational methods, the quasi-causal methods, they get a bad rap. Why do you think that is?
So I think part of the reason for that is because of the lack of standardized template. Template's not really the right word, of a standardized protocol for how to follow it. So observational methods historically can vary quite differently, and it's kind of up to the researcher and the research team of how rigorous are we going to be, thinking through things of when are certain criteria met or not met. In recent years, that gap has been closing a little bit. There's a concept known as emulating a target trial. So basically, you try to conduct the ideal RCT using observational data. So there's things you obviously can't do, like you can't randomize a patient, but you can fit a model, like use a propensity score model or use a different method. So I think part of the reason that there's been a bad rap in previous years is because of that lack of a standardized process. Whereas in an RCT, you know that patients are going to be vetted for inclusion and exclusion criteria, they're going to be randomized. It's a very that's not to say that they're without challenges. Each RCT is different. I think that's where it mostly comes from. And that lack of standardization can lead to biases. So a great example is if you're not careful, then in an observational study, there can be a mortal time bias if you're looking at a time to event outcome. Whereas typically that's by design, that's not as much of a problem with RCTs.
Okay. In my field and even in econometrics, we are always, handicapped by the data that we have, and we can't do RCTs because, I can't put a bunch of people in a single room and say that, here's advertisement that you're going to looking at for the next week and nothing else. Of course, they will not agree to it, and there is not going to be adherence to it. Similarly, for let's say economics, if you're adopting some policy in a particular city, there are definitely going to be transfer of people from one city to another, and then again you can't have adherence again, right? So we are kind of handicapped with respect to that, and we are just left with the quasi-causal methods. At least I have been struggling to convince some clients saying that, hey, we can't do RCTs in marketing, but quasi-causal methods are no less either. I think your explanation adds a lot of support to that a well done quasi-causal experiment is still as good as RCTs.
Absolutely, and it's a use case basis too. Like for us, the reason RCTs are used is because we can't just approve a drug without any
Mm-hmm.
evidence and have
Mm-hmm.
people start taking a drug and hope that it then assess it after the fact, because there's the other side to that of adverse effects. Like in the research that I do, for example, for my PhD, looking at adverse events, you can't do an RCT. RCTs do capture adverse events, so those would be side effects, like things that you wouldn't expect, or effects that are harmful. So it really depends on what the use case is. I think observational studies often get more of a bad rap than is probably deserved. Each study should be looked at on its own merit of how well it was designed, rather than just because it's a certain study design, it's inherently good or bad.
Great. One of the posts that attracted me to your LinkedIn profile was that assumptions of causal inference, right? Can you explain the key assumptions of causal inference? Those are exchangeability, positivity, consistency, no version of treatment, and no interference. I believe the last three can be clubbed together as satwa. But yeah, please go ahead. Yeah.
Yeah, absolutely. Yeah. So exchangeability. So in epidemiology, we talk a lot about confounders. And sometimes the term is used, the same thing is meant, but different terms are used by different fields. So a confounder in our field is a variable that causes both the exposure and the outcome. There's a little bit of nuance that there can be confounding, which is basically association can go from the outcome to the exposure variable through a pathway. And what we want to do is we want to make sure that that's not possible, because what can happen is you can have these spurious correlations. So it looks like there's an effect, or it looks like there's no effect when there really is. So exchangeability is making sure that the groups that you're blocking that pathway, so you're blocking that flow from the exposure to the from the outcome to the exposure. In an RCT, that's done through randomizing. So the best example is through an RCT. And when you randomize patients, there is nothing that causes someone to get the treatment. It's random. So you don't have to worry about that. In observational data, you can use like an outcome model. So you're modeling what the outcome is to adjust for that. You can model the exposure to account for that. So it's to make sure that those groups are exchangeable for those confounders. So it doesn't matter if there's, well, it can matter for other reasons, but the assumption to be met, it doesn't matter if there's more, say looking at whether monsters enjoy coffee. There can be a different kind of monster if it's not a confounder in one group versus the other, and that won't have as much of an effect. It's really for confounders. The second one is positivity. So positivity, again, in an RCT, it's inherently met because everybody that is in the trial, in order to be randomized, you have a chance, a less than zero chance of getting treatment. Otherwise, it wouldn't be random. You'd know what it was. So positivity is something that needs to be checked with observational data. So when you're fitting a model, you want to make sure that people can have a probability between 0 and 1 of receiving treatment. It's really greater than 0. That's the problem, because you know that somebody can't receive treatment. That's positivity. Consistency is a little bit of a tricky one, or at least I found it was. It has to do with if the person actually receives treatment, then their observed outcome is their potential outcome under that treatment. So it's basically linking the data that you have to that treatment. So the reason that consistency, no version of treatment, and interference are all tied together is because it has to do with you defining your treatment. So that kind of leads into the no versions of treatment. If we say, does coffee cause happiness? Or coffee maybe is a bad example. If we say, do hot beverages cause happiness? Are we talking about tea? Are we talking about hot water? Are we talking about coffee? About I don't know why, but like a hot
Chocolate?
smoothie?
Yeah.
Yeah,
Yeah.
chocolate. Thank you. Good example. So you want to be very clear in what exactly you mean, and that's why often in clinical trials they'll be as you want to leave as little ambiguity as possible. So it'll say like this is the dose for this duration in for these patients, to make sure there's no versions. Because if you say, okay, hot beverages do cause happiness, but does coffee, does tea? So that's where it kind of blends together. And the no interference. This one is that a patient's treatment status can't be affected by another treatments. So this isn't met when you have things like vaccine studies, or not vaccine studies, but when you're looking at exposure to different diseases. So, for example, COVID was a big one. You can transmit that to somebody, so that assumption wouldn't be met. And there's methods that are different that can account for that. But typically for the work that I do, that's never really a problem.
Great. I think those are great explanations of the assumptions of causal inference. Uh, why is temporality so important in causal inference? I know you talked about does coffee cause happiness.
Yeah,
What if somebody's already happy and they drank coffee and they're still happy? Or let's take the
exactly.
example of a classic chicken and egg. I think in one of your posts you
Hmm.
have that image depicted. So please talk
Yep.
more about it. Why is
Yeah,
temporality
yeah.
so important?
Yeah, great question. So, I like to call it kind of the chicken or egg bias,
Mhm.
that you don't know. So, for example, if you do a cross-sectional study, so you slice the data and you get there's these participants in your study, but you have no idea the timing of the variable. If I have coffee and then I become happy, that's very different from if I have happiness and then I drink coffee, or if I tell you that I had coffee and I was happy, but you have no idea what happened. Like the causal, for cause and effect, in order to know something's a cause, it has to happen before there's an effect. So that's why temporality is so important, because you really need it in order to do causal inference. There's some arguments that there's ways around it, but I think that's the consensus is that you need to have temporality. And that's not to say that other studies that don't have temporality aren't useful. So, for example, for my PhD, one of the parts is doing a cross-sectional study, which has then informed the second part of looking at causal inference a bit closer, because you can find out kind of like a hypothesis generation of is this worth looking at more? But temporality you really need in order to do causal inference.
One of the reasons that I follow, biostatisticians, epidemiologists, and even clinical trial people on LinkedIn is because the way you guys apply statistics is so much rigorous, right? I wish my field of marketing, applied statistics to that amount of rigor, but yeah, sometimes I think it's a wishful thinking, but, I keep that endeavor going on, like through my posts on LinkedIn and blogs and everything. You explain a lot of statistical concept with a lot of clarity, right? So I have a bunch of statistical concepts. If you can help clarify for our audience, that would be great.
Sure, yeah.
So let's start with, p-value. How would you explain p-value in a layman term or in, a in-depth? No problem. Yeah.
Yeah, very good. So the p-value from like a textbook definition is the probability of a test statistic, at least as extreme, based on the null being true, which to me is a mouthful. The p-value is the way I look at it is how interesting is this result if we assumed that we shouldn't really see much of a result. To me, it's the same as like if someone said it's going to be nice weather tomorrow. Um, okay, well, I need a bit more information than that. So it's useful, and has its place, but sometimes I think it's overused, and I don't think I don't think it's inherently a p-value problem. I think it's a byproduct of when there has to be sometimes a decision made and there has to be a cut point. There is in everyday life. Like if you go to a physician's office and they say you have high blood pressure, there is a cutoff that's chosen. But sometimes I think the word probability gets used when it should almost be not used with it because that causes a lot of confusion. So one thing is like what's the probability that our result is true? What's the probability about the null being true? But it doesn't really have anything to do with that. It's how likely our result is if we wouldn't expect to see a result. That's kind of but I think oftentimes because of statistics, I love statistics, but some of the naming conventions for things are backwards from everyday life. So my favorite example of that is probably likelihood. When I started learning about statistics, I thought likelihood is how likely something is. So, but it's not. So in everyday life, if I said how likely is it for me to get a cup of coffee, I'm talking about probability. But in statistics, you're talking about a abstract number based on a statistical model. So I think that's sometimes where there's a disconnect with some of these concepts.
Yeah, I think I agree with your explanation. I mean, the way I say p-value, it is just the probability of just observing the data given your null hypothesis. And of course, we assume that the null hypothesis is, true. But there are so many misconceptions, right? People think that, hey, p-value should only be 0.05. It cannot be anything else. That's another big misconception. I want to ask, in the field of biostatistics, in the field of epidemiology, do you use a different cutoff? I'm pretty sure you must. Like, it's not just 0.05, it could be 0.01 as well, right? What are your
So it
comments
really
on that?
depends. Yeah. So that's a great question. So it really depends. It depends on the study that you're doing, on the sample size, the effect size that you're expecting to see, and this is kind of where power plays a role. So, for example, often 0.05 is the cutoff that's chosen, especially for RCTs, in my experience. But as the sample size grows, that needs to be accounted for. It also needs to be accounted for if there's going to be multiple tests. So if you're testing a bunch of different things that needs to be accounted for. So, for example, for my PhD, I came across this last night with some results. There's 300,000 people in the study that I'm working on. So the p-value is so small that if it was 0.05, like for me, it's more about the effect size than it is the p-value at that point. But it really depends on, so 0.05 is not popular, is a common one. 0.01, less common is 0.001, but it really should be a function of the sample size and what kind of power the study has tied to sample size. But 0.05 is still, I'd say, the most commonly used cutoff.
Yeah, I think you touched upon effect size, and I have heard a lot of epidemiologists and biostatisticians talk about something known as MCID, minimal
Mhm.
clinically identifiable effect, or
Mhm.
something like that. Am I right on the acronym, or what is MCID?
Very close. Minimum clinically important difference.
Okay.
So that kind of ties into like sometimes I think to tie back to your question about p-values, sometimes just because there's a difference between statistical significance and clinical significance, um, if we find out that our coffee is statistically significant in terms of the temperature, that might be 0.01 of a degree, and we may not care about our coffee being that much hotter. Um, so yeah, so that's where it comes into play.
I think in my area, it will be something known as MBID, minimal business identifiable, because
Yeah.
it may not be clinically identifiable, but just for business.
Yeah.
That'd be good. Yeah.
Yeah, and the exact same thing, like if you find a statistically significant difference, but a client, if you see that the effect, it's not going to, if you implement a certain solution, then it's not going to change substantially or noticeably. Then that's, so it's the same concept.
Yeah, I'm going to use, MBID, minimal business identifiable difference, to all my stakeholders going forward. Yeah.
Yeah,
Talking about
perfect.
zero point zero 0.05, right? I mean, a lot of people think, hey, how did it come about? I have read a lot of statistical textbooks, and, R.A. Fisher said that, hey, it's because of 1 in 20. Do you accept a 5% error of getting things wrong? That's all about it. That's why it's 0.05. And this opens the door to, type 1 error and type 2 error. Can you talk more about, these types of error, and which is more grave in your field? Is it to do type 1 error or type 2 error?
Yeah, so that's a great question. So they're semi-tied together, but a type 1 error is the probability of saying, so when you say that there's an effect, but there's not. So you say, okay, this treatment does work when in fact it doesn't. And the type 2 error is kind of the flip of that. It's if we say there's no effect when there is. So you're basically missing out on a potential treatment. So really this boils down to like type 1 is more um, is treated with more caution in our field because you could potentially be exposing people to a treatment that doesn't work when you say that it does, and that has side effects associated with it. So if someone was exposed to chemotherapy, a certain type of therapy for cancer, and there's a laundry list of horrible side effects, but the treatment doesn't work. It's pretty important to make sure that that probability is as low as it can be. Whereas if you miss out on a potential effect, then it's more lenient in that sense. It's basically we would prefer for the safety of people to miss out on a potential treatment than to expose people to something that's not helpful. Um, I don't know if it's the same in business or in your field.
Yeah, I mean, we kind of, at least I can speak for my company, we adopt frequentist methodologies because it kind of gives you the type 1 error guarantees. I mean, that's all about false positive, right? So you're trying to safeguard against false positives. In my
Mhm.
field of, market mix modeling, we are trying to identify the marketing channels, which has, caused the sales, right? And we don't want to identify, false channels. And if we do so, the clients would end up putting their money on, channels that really didn't move the needle of sales and end up losing money. So we kind of, safeguard against that and use, type 1 error guarantees. But in your field, if I'm given to understand, let's take an example of COVID, right? Uh,
Mhm.
if we falsely develop a medicine or a vaccine and assume that it's working, but it doesn't, I believe we are committing a type 1 error. And you think that this is much more grave because then there is a very virulent disease out there, people are dying. But if they take a medicine which falsely gives them a hope, but still it doesn't work, you're still going to end up seeing the fatalities that you keep seeing. Is that the right thought process?
Exactly. Exactly. Yeah. Yeah. So it all boils down to like harm reduction,
Mhm.
to not harm people. I mean, obviously you don't ever want to harm people, but there's no treatment without risk. So it's to mitigate that risk. So that's exactly
Mhm.
right.
Great. So moving on to the next statistical topic, confidence interval. I had a
Hmm.
lot of fun, talking about this on LinkedIn. Just, a couple of days back, I saw somebody in my field, get the interpretation wrong. One of the funny interpretation was that, hey, the lower bound is minus 250K and the upper bound is positive 250K. And so this person thinks that, it could range between something like, TK to 550K. I believe
Hmm.
this is a totally erroneous understanding. How would you explain confidence interval to people?
Yeah. So confidence intervals, they're a bit bizarre in the way that they've came to be. So confidence interval is a range between where you think the true value is, and if you were to repeat the study over and over and over and over for each study getting an interval, 95% of those intervals um, would contain the true value. So sometimes I think a misconception, and I was guilty of this when I was first learning statistics, it has nothing to do about the probability of it being in that interval. It either is or it isn't. So if we take like some numbers and say confidence interval of 1 to 3, is number 4 inside of it? No, there's no probability. It's either yes or no. So I think sometimes the 95% aspect um, gets misconstrued. I think it would be probably a bit more helpful to remove that and say this is the interval that we think the true value is within, somewhere in here. And then in the methodology section, say we used a we used a 0.05 as the cutoff for type 1 error in our. That's why our confidence interval is 95%, rather than anything to do with probability.
Yeah, that was a great explanation, and I think that clears out all the misconceptions with respect to confidence interval. Uh, uh, as I told you, there are a lot of misconceptions about confidence interval in my field, and I just gave a simple example of that. Uh, why do you think people get all these frequentist concepts wrong? Do you think is it poorly taught or is it poorly understood or both?
So I think it's a couple of things. I think I don't think it's necessarily poorly taught. I think it's no different than any other subject. Like there's some great resources, there's some that aren't. One that I would highly recommend for anyone interested in statistics is there's I believe it's called Seeing Theory by Brown
Mhm,
University, and they have great visuals to help understand all this.
mhm.
I think part of it is that statistics use coming from a different field of engineering, the field uses some terms that are a little backwards, or it's a trade-off of understanding versus being 100% technically accurate. So using like 95% confidence interval, the minute you add a number in there, people will interpret that in a certain way. Um, so I don't think it's necessarily poorly taught. I think uh, sometimes what happens too is it's exciting when you see results, and it's hard to not overinterpret. I think that's probably something that I see the most is interpreting results or extracting beyond what they mean. Um, but I think everybody can use like the more that I learn about statistics, the more that I realize I don't not don't learn that I don't know. So there's always things to learn about it. But I think it's a bit of both. Yeah.
Yeah, I mean, when I think about, the frequentist methods, I mean, I've heard people say that, hey, you know what, it's not intuitive to me. But I think frequentist methods were not developed for the layman, right? It was developed for scientific inquiry, where, scientists would know what to do with it. For example, they are not trying to prove a hypothesis, but rather they're trying to, negate it through the principle of falsification. That is the line of thought, the ideal scientist would take. But lo and behold, general public, they see 95% confidence interval, and as you rightly said, they misinterpret and think that, hey, there's 95% probability of something happening. So I get, where the misconceptions arise, but I think rather the people should think about, at least with respect to confidence interval. In my field of market mix modeling, I tend to think of it like an apparatus that is trying to capture the true parameter. Is your apparatus good enough most of the time to capture the true parameter or not? It's not a commentary about the uncertainty of the parameter per se, but it's more about how well your apparatus or experimental design has been built. Would you agree on
Yeah,
that?
I think that's a great example. It makes me think of another analogy. A confidence interval is a bit like a fishing net. If you put
Yes.
a fishing net in the water, is the fish in the net or is it not in the net? And then take it out. And then once you lift it up, it either is or isn't. There's no but yeah, and I think frequentist sometimes the other thing is it's great to be as accurate as we can be and reduce bias. But sometimes I think it's important too to understand as I've learned more about statistics to understand the magnitude of something. So when someone says this result's going to be biased, by how much? Because again, that's one similarity between engineering and epidemiology with statistics is we in civil engineering we love squares and rectangles. So you try to like, is this an approximately a square, approximately a rectangle, when you're designing a concrete structure? And nothing is really ever a perfect square exactly. It's pretty rare. So in statistics, like, is it close enough? Is it good enough? I think that's important too. Yeah, it's a great question.
Yeah, I think earlier you talked about, we humans seeing things in black and white. There is always a tendency for our humans to, seek a shortcut and, try to see things black and white, like set a threshold and say that, oh, anything below this threshold is something, anything above this threshold is something. And because of that, nature of us, we kind of, artificially, bring in thresholds where it shouldn't be brought in, right?
Yeah, and I think it's a great point that you bring up too. Like, we can't discount the decision makers. Like, I think Bayesian methods in my field have a lot of benefits in the right context. But I also understand if you're a physician working in an office, or if you're a business leader, you have to make a decision. Like, if I was a physician, a patient comes into my office, I can't look at the patient and say here's the bounds on whether it'll work, and there's this much probability. The patient, am I prescribing the drug or am I not prescribing the drug? So I do understand both sides to it. And I think sometimes some of the debate comes from let's remove p-values and add a different approach. But there's a great article from in my field, a famous statistician, Andrew Gelman, who discusses like the problems aren't just with p-values; they're with basically any cutoff. So it doesn't matter what you're using, any single number. Um, I think it's a great point.
Yeah, I
Here we
think
go.
another excellent scientist, I think his name is Frank Harrell. He also talks about,
Hmm.
the artificial thresholds. Maybe I'll just drop a link to both Andrew Gellman
Yeah.
and as Frank Harrell's, in our podcast.
For sure. Yeah. Frank's a fantastic resource.
Yeah. Yeah, I enjoy his commentary on artificial cutoffs, and it has served me really well in my data science career because I kind of know, for example, logistic regression. Earlier, a lot of people have this misconception that, hey, you know what, it's a classification algorithm, but what it outputs is a continuous probability, and we as humans want to see things black and white. We put another
Mhm.
threshold like zero point 0.5 and say that, hey, anything above zero point 0.5 is this, anything below zero point 0.5 is this. But actually, I was lucky enough to work with the banking industry early on, and they were using logistic regression not as a classification, but as what it was intended to be, a set of probabilities. But of course, they used to bucket those probabilities, saying that, hey, if it's 0.8 to 1, these are like highest probability of people who are going to default on a loan, or it's like zero point 0.7 to zero point 0.5, they are a medium risk and stuff like that. But they are not creating an artificial threshold there. They're bucketing the probabilities. I think bucketing is fine rather than drawing a
Yeah,
strict line.
for sure. Yeah. And the other thing too to that is one of the things, especially with observational data, to go back to an earlier question, it's when you have, and I don't know what it's like in your field, but with us with RCTs, you have to pre-register your protocol. So for example, if you're submitting to the FDA, you have to register, I think for any RCT, you would register with clinicaltrials.gov and upload your protocol. So we know a priori, this is what you had hypothesized, this is what you're testing. Sometimes with observational studies, that's not done. So I would like to think that people are honest and mean in good faith, but sometimes it's things are ran multiple times, or they're using p hacking without realizing they are to reach that artificial threshold. So pre-specifying what you're going to do helps a lot too, to prevent kind of those use cases.
When you say pre-specify, is this something to do with the significance level? Like you can't,
Just saying this is what we're going to do. This is what we're going to do before we ever see the data.
okay,
So
okay.
in an RCT, you also don't have the data. So like you can't make like you're kind of forced because you don't have the data. In observational data, the data is there. So but there's ways around that. Like companies will restrict access to people who are working on the data and only give it to them once a protocol has been written. Or only the Orton study before where we looked at the covariates and the treatment variable before ever seeing the outcome. I think that's important too, is to pre-specify what your hypothesis is, what you're testing, what the cutoff is, and then kind of adhering to that
I mean,
cutoff if that's the decision.
since we're talking about experiments, what is exactly an
Mhm.
experimental design, in epidemiology? How would you go about explaining
Yeah.
it?
Yeah. So that's a great question. So the way that I think of an experimental design is when you have like a structured plan for doing research,
Mhm.
and you really want to know like the cause and effect relationships between variables. So that is like the whole scientific process, kind of formalized of the hypothesis, what's going to be your independent variables. In epidemiology specifically, we use an acronym called PICO, PICO. So P is population. So who are you interested in? I is the intervention, C is comparator, and then O is outcome. So what outcome or which outcomes are you interested in? So it's kind of like the scientific process, but in an experimental framework.
Mhm. I think we have come a long way since our earliest, experimental design designed by R.A. Fisher. I think it was the field experiments. He wanted to see the crop yield whether, one set of crops yielded better once they were administered fertilizers and the other set was not administered fertilizer. I think it started from there, right? Uh, in your blog, I also came across this hierarchy of study
Hmm.
design. One thing that was really surprising to me was, the meta-analysis is at the top of the pyramid and
Hmm.
RCTs is in the second rung. Can you explain like why is meta-analysis, at the top of the pyramid and not RCTs?
Yeah, so that's a great question. So the reason in my field is because to with science to take an individual study and assume that that's the ground truth is it can be a fool's errand. So it could be correct, but we need to replicate. Like replicating science is a huge part of science, or is it's much easier said than done. If someone conducts a $5 million trial, asking someone to replicate it just to replicate it is is a big task. But meta-analysis, in particular, taking a bunch of RCTs and combining them statistically, it really helps to paint a broader picture. Now, there's some issues like just like an RCT, a well-conducted meta-analysis is extremely useful. And so when you're including different studies in a meta-analysis, you want to make sure that there are similar studies in terms of who are they targeting. Were these studies conducted? Are they well-conducted studies? Are they all well-conducted RCTs or observational studies? So it's basically that compiling of a bunch of different studies together, and here's what the result is. So there's some statistical methods to do that, and then you kind of get to see what the overall result is from a bunch of different studies. Because it gets tricky if you have three studies, one says yes, there's an effect, one says no, there's not an effect, and a third says yes, there's an effect, but it's small. Which one is right? Which one is correct? So that's where meta-analyses can help out.
Mhm. Uh, in your field, I have come across this word called RWE. I
Mm-hmm.
mean, to the uninitiated, what is RWE? I think it stands
Yeah.
for real world evidence. Can you talk
Yeah,
more
yeah,
about
for
this?
sure. Yeah, great question. So it's the same thing as an observational study. But the difference that I personally think of is when I think of RWE, I think of emulating a target trial, more methodological rigor. So it is still an observational study. It's kind of rebranding in that sense, but using more nuanced methods. Because we've learned a lot with observational studies in the recent years. A lot of great work by Miguel Hernan, Jamie Robbins, Anthony Matthews. There's a lot of people working on that. That's what RWE is. So there's a few different resources as well. I think it's the National Institute of Health Care and Excellence in the United Kingdom. They have a guideline for RWE. The FDA, Food and Drug Administration in the United States, they have a guidelines for RWE. It's basically generating evidence using observational data.
Hmm?
Yeah.
Okay. I think in one of your posts, you also talked about Bradford Hill's criteria, whether it's still relevant or isn't relevant. I mean, a
Mhm.
lot of people don't know this, but the smoking causes cancer was not proved through RCTs, but through Bradford Hill's criteria.
Mhm.
And perhaps if we were to roll the clock forward, perhaps we might be using RWE. Am I right on that?
Yeah, for sure. Exactly. And that was actually one of the things that one of the reason I got into causal inference was through reading Causal Inference What If. It's a free textbook by Miguel Hernan and I think it's Jamie Robbins. Um, James Robbins. But I always wondered, like, at what point do we say that smoking causes cancer? Because similar to a frequentist approach, at some point, if there's overwhelming effect sizes, then we need to look into that. Like at some point, because there's no magic threshold where there's a celebration about yes, there not a celebration, it's a bad thing, but there's no like definitive now we know that there's um, a causal effect of smoking. But now today we know that's pretty common. So that's how I got into it was that exact thing, was wondering at what point in time do we say yes, smoking actually does cause cancer? And Bradford Hill's criteria, I believe recently I learned that it was meant to be more of like a discussion. But I also understand that while a lot of them may not be relevant today, that was also quite some time ago. And I would be alarmed if things don't improve in science over 60, 70, 80 years. But I do think there's parts that are still useful, but there's some that maybe we need to reconsider.
I mean, just playing a devil's advocate for, real world
Yeah.
evidence. I mean, on one hand, you have RCTs that is a really pristine setup, there's
Hmm.
very little that can go wrong if you do it right. But real
Hmm.
world is messy, as you know, right?
Hmm.
What is the veracity of, reports or results coming via RWE? How much can
Yeah.
we trust it?
Yeah. So that's a great question. So I think there's a few things. One is what's the research question? And could an RCT have been done? If not, why not? So for example, smoking. Pregnancy is another one that RWE is used a lot for because you're not going to expose pregnant women to something that's dangerous. Also with RCTs, oftentimes they're designed in their sample size calculation to test for efficacy. So they do record adverse effects, but they're not testing adverse effects as their primary endpoint, because that wouldn't be ethical. So I think the veracity really depends on how well the study was conducted. So we absolutely can take data from RWE. And this is one of the other things that in recent years there's been a lot of great work on. There's not limitations. So there's assumptions that have to be met. Take exchangeability. So confounders. RCTs in theory, if it's done appropriately, just for measured confounders and unmeasured. RWE is only measured. However, we can do sensitivities for unmeasured confounding. So we can find out how much would we need in order to change this result. A quantitative bias analysis of here's the actual number that you would need to make these results not what they are, or to change them to be null if there's an effect. So I do think that we can absolutely use RWE. Honestly, that's what 98% of my work is on, both my work and my PhD. So I think we absolutely can. It just requires a well-conducted study. One thing to improve that is following a target trial emulation approach. So like to write a protocol, what would be ideal in an RCT, and then how well can we do that in RWE, so in our study. That helps tremendously because it also helps with timing of variables, like making sure everything's before treatment for inclusion exclusion criteria and all those sorts of things.
Yeah, I mean, when you're talking about, RWE, there arises the concept of, a conditional effect. Things have condition on so many things. Whereas when you have RCTs, perhaps it is more marginal compared to, RWE. Can you talk to the audience about, the difference between a marginal effect versus, let's say, a conditional effect?
For sure. So a marginal effect is when it's not conditioned on anything. So like if you think of the way I found it easiest to think about it is if you think of an equation, it would be y equals x versus y equals x plus age plus sex plus. So they're very relevant because certain effect measures they will be the same. Others, the measurements won't be the same, even if a variable is not a confounder. So for example, say that we have coffee and it does cause happiness, and we have a variable temperature. Temperature affects happiness, but it doesn't affect whether you get coffee or not. If we adjust for temperature and use logistic regression, that effect will be different than if we don't adjust for temperature. However, if you use a risk difference, so a continuous outcome, those effects will be the same. So it's important to keep that in mind, like what exactly we're interested in. Oftentimes in my research, it's conditional effects. And there's also ways, Adrian, I'm gonna try to pronounce the last name, Olszewski, maybe.
Yeah, 18 Solzewski, yeah.
Yeah, he posts a lot of good stuff about that online, and there's different like packages in R you can use. I'm sure there's equivalents in Python and other languages.
Great. Let's talk about causal estimators versus causal estimands. I'm
Yeah,
pretty sure it's just more than a nomenclature. There is a deep difference between the two.
yeah.
Please talk about it.
Yeah, for sure. So the causal estimand is the what. So what do we want to estimate? We want to estimate the effect of copy, unhappiness in green monsters, or whatever your research question is. Who are you trying to make inferences about? When you use inferential statistics, you're inferring stuff. So you're trying to make an extrapolation. And who is it that we're interested in? So it's the what slash the who. And then estimators is the how. So how are we going to do that? It's the statistical model. So like a very common causal estimator or an estimator in general would be like linear regression, generalized linear model. Not really sure why, again, in statistics, they use the term estimator.
Mhm.
I would have preferred like statistical methods, but maybe they There's
My
some rationale behind
yeah, my
that.
best guess is to, estimate a parameter.
Yeah,
Maybe
yeah.
it is something about that because, whenever you have causal inference or, in my field, you cannot have a parameter. All you have is the sample, and you got to make inferences about a population just based on the sample that you have. So I think
Mm.
all you have is the statistic at hand, but you're trying to say, hey, whether the statistic is somewhat equivalent to a parameter or not. I think that's how, this
That's a good point.
nomenclature.
That would make
Yeah,
sense.
yeah. Yeah, talking about causal estimates, right? I have seen people stop at ATE, that is average treatment effect,
Mhm.
but I'm pretty sure there are more to it. Like there is ATT, average treatment on the treated, and then there is ATU, average treatment on the untreated, and there is
Mhm.
also conditional ATE. There is also LATE. There's so many things, right? Do you
Mhm.
think people should, explore more of this rather than being stuck with only, average treatment effect?
Absolutely. And that's a great question. So I found fantastic papers by Noah Griefer, I think that's how you pronounce his last name, and Elizabeth Stewart, um, talking about causal estimands, and they give very concrete examples of what exactly would be the question with ATE. The way that I viewed them at first is who's receiving weights if you're using inverse probability weighting. And how the population changes. So if it's the ATT, it's the average treatment effect in the treated. So it's people who are similar to those that are treated. One thing that I realized about a month ago, what can cause some um, misconceptions is that in an RCT, because you're randomizing the patients, the ATE, the ATT, and the ATU are often all the same because the patients are similar already.
Yeah.
So if you think about observational studies, it's, well, these treated people could be quite different. So again, with my PhD as an example, we're looking at benzodiazepine use, and the people that are prescribed benzodiazepines are as a high proportion of females and they're older. So do we want to know people like that? Are what we're interested in, or is it more people who are not treated? I think people should explore further what exactly is the question that we're asking and what would be the appropriate estimand for that.
Mhm. Yeah, I think this also somewhat relates to, inverse probability weighting. Can you explain to our audience, what
Yeah.
is it exactly? What is IPW?
Yeah, yeah, for sure. So I didn't learn that in school. I learned that after at my previous job, and I think it's a fantastic tool. So inverse probability weighting, most people are familiar with matching, or propensity score matching in particular, when one-to-one propensity score matching. So you have a pool of participants and you're trying to match an individual to that group, somebody from that group, and you do that over and over and over until you have ideally everybody matched or an acceptable proportion. Inverse probability weighting is a little bit different because what you do is each person gets a weight. So people are either upweighted, so they have a weight greater than one, or downweighted based on how similar they are. So if someone was perfectly similar to the other group, they would have a weight of one because they're, if you're using stabilized weights. Yeah, if you're using stabilized weights, I think it'd be one. But it's helpful because when you reweight those patients, there's this concept of a pseudo population. So when you multiply um, each person by their weight, their propensity scores would overlap, so they'd be the same. And the reason that it's so beneficial is because with matching, you often lose patients. So if you're doing a study with 200 people that are treated, you might need a group of 1,000 or 500 for the controls because you're going to lose people. And once you match, you're dropping people only because they didn't match, which introduces like a selection bias and also kind of changes where you're making your inference about. Because those patients that you include in your study that seemed reasonable to include are being dropped just because they don't match. So IPW is great for that. And there's IPW can also estimate every different estimand. So like ATE, ATT, ATU, ATO. But you're basically applying a weight to the person based on how similar they are.
Yeah, that was a very insightful explanation. Earlier in the talk, you talked about DAG. directed acyclic graphs. I have
Mhm.
talked to a lot of econometricians. I have also talked to epidemiologists. My belief is that, generally econometricians do not have a favorable view towards DAG, but whereas, epidemiologists have a much more favorable view. Perhaps, it's because, econometricians feel that, hey, it's a slippery slope. You can just draw a DAG and try to fool people saying that, hey, we have established causality. But I'm pretty sure epidemiologists, go through a lot of grind before that. And then it's a ultimate step to, just showcase the understanding of, what you have gone through rather than, it being a pre-step. Where do you stand on this debate? Do you find DAX useful? Or do you just consider it as a hypothesis generating mechanism? Or do you think, yeah, DAX definitely prove causality?
Yeah, so I think DAGs are I think they're quite useful, but I do think it's important to keep in mind that they're assumptions. So we're assuming that this DAG is correct, and every analysis that follows afterwards, we're assuming that's correct. Oftentimes, when you ask, if you were to ask someone why they included a variable in a model, uh, they may say because we think it's a confounder. Well, that's an assumption too. You are assuming it's a confounder, but it might not be. So I prefer for the assumptions to be explicit, to be we're assuming this. And then it lets people critique it. No DAG is going to be perfect. It's probably not going to be 100% correct, but if it's correct enough to estimate the effect, or if it also allows people to contextualize the results. So if I see a DAG and then results, but there's something in the DAG that I notice I don't personally think makes sense, then that lets me know rather than ambiguity or being opaque. I haven't really talked to an econometrician about it before, so I'd be curious to hear what their critiques are of it. Keep in mind that it is an assumption, just like anything.
And there's a famous blog, where Guido Invents and, Judea Pearl, they kind of debate
Mhm.
each other, why DAX are better or not. That's an excellent blog for anybody to read. I'm not taking sides, but, you can have, both the sides presented very well, and people might find it interesting. I'll leave the comment to that,
And I think it's very important too. Like
yeah.
I do think it's important to keep in mind that DAGs are assumptions. Like they're not. If someone were to say this DAG is 100% correct for a fact, don't question me. Well, then I'd have a problem with that as well, because it's not how science works. So yeah.
Yeah, talking about causal assumptions, right? So I play this game with all our participants. So here's a small game where, I would ask the participant to rate the reasonableness, unreasonableness, or the impossibility of a particular causal methods assumption. So let me share my screen and we can, get started.
Sorry.
And you can preface, through an example, like, for example, you can talk about this technique before, giving your verdict, whether it's a reasonable thing or an unreasonable. Yeah, I hope you can see my screen.
Yeah. Yeah.
Yeah, so let's start with the propensity score matching, right? Since you are an expert in that, what do you think about the perfect balancing assumption in propensity score matching? Is it a
Yeah.
reasonable assumption, unreasonable, or impossible?
So I'd say unreasonable, only
Mhm.
to be pedantic, because perfect balance, I would say no, not so much. Like there's going to be some degree of
Mhm.
imbalance. It's more about adequate or reasonable balance.
Great. Uh, let's talk about the sattva assumption in biostats or real world evidence. Where do you stand on that?
I'd say that's reasonable.
Mhm.
Um,
Can you talk more about it? Like, why do you
yeah,
think it's
yeah.
reasonable?
So I'd say that it's reasonable, because in order to adequately answer the question, you need to leave it so that there's no ambiguity in defining your treatment. And I think that's a reasonable assumption. And when I say reasonable, I mean, um, how well should we, like, how strict should we be about it? Like, I think that assumption should be met because it's reasonable. Whereas perfect balancing of like an SMD of 0.00000 isn't going to happen, most likely.
Mhm.
Um, so yeah.
Okay. Next is the difference in differences parallel trends assumption. just to let you know, we in marketing use this a lot because,
Yeah.
first of all, it's very simple to do, but it's much more simpler to explain to stakeholders too. But of course, there are so many advanced functional forms to it. Like for example, staggered events and all that. And I'm pretty sure the recent paper from Pedro Santa Ana, Scott Cunningham, Baker et al., they have published a really excellent paper, and people should really read it. But where do you stand on the parallel trends assumption? If you can preface through a small example of what is that assumption, first of all.
Yeah, so my understanding, and we don't, I think we use something similar, but not exactly the same. So my understanding is that the trends, when you're using different, they have to be parallel, so like the lines can't be crossing between the two groups. Um, I think this one, I would put it like in between reasonable and unreasonable. So I'll say
Mhm.
reasonable, with the caveat that it really depends on the study.
Mhm.
And I've seen arguments that I agree with about it being unreasonable, but I think it really depends on the study and what you're referring to. So, for example, there's the assumption, and with all these assumptions, my view is it's mostly not going to be met 100%. So, like, what degree of it is okay? So, the best example in my field would be Cox proportional hazard. So the proportional hazards assumption is that the hazards are proportional over time. So my understanding is that's fairly similar to the parallel trends assumption. Um, so it's not that like it's always going to be invalid, but it's like that degree of um, how valid is it, if that makes sense. So
Yeah.
in between reasonable and unreasonable for the parallel
Okay.
trends,
Okay.
but it depends on the
Sure.
outcome. So
Okay. There you
somewhere
go.
in the
Yeah.
middle, both.
Yeah. What about synthetic control methods, synthetic twin assumption?
Yeah, so I don't know that assumption as well. Is that the concept of generating a synthetic twin and then having a different outcome for them?
Yeah, so I can
Or two
explain it
sequences?
in my field of marketing. Whenever you don't have a control market, what you try to do is you try to create a synthetic control market by, kind of like hodgepodging together various markets. Like, for example, if I'm running a test, I have a test market that is New York, but I don't have a control
Mhm.
market. Maybe what I'll do is I'll just pick up California, I'll pick up Texas, I'll pick up Alaska, bunch them together, and, create a synthetic control group. It is not existing in reality, but it's just made up.
I gotcha. Yeah, so I'd actually put that one in between as well, only because to me how reasonable that is depends on the area. So that seems like it's useful in different fields, but in my field, I don't think that would be met with the same. I think it'd be met with a lot of criticism.
Okay.
um,
Uh,
because of like differences that are hard to control, like genetic differences that we wouldn't have data on. Um, that'd be, but yeah, but I don't know enough as much about it as the first two.
yeah, fair
And
enough.
same thing with this next one with sharp cutoff rule. I've seen regression
Fair-
discontinuity designs,
yeah.
but I don't know about that rule.
Okay. So we'll just leave it at that.
Yeah,
So we will not put it into any bucket. But yeah, this has
sure,
been great, Ryan. So I'll just pause with this particular segment and we'll go on to the
sure,
other questions.
sure.
Yeah. Yeah. So I think we're just left with a few more questions. I promise not to take
Yeah.
much more of your time.
No, no, it's fine. Yeah.
Yeah. Uh, so talking about programming languages, right? I have seen, econometricians use Stata more. Uh, is there a particular programming language that epidemiologists or, biostatisticians use more for causal inference? What has been your
Yeah.
experience?
So there's a variety. My take is that programming language, it's the best tool for the job. So this is a crude example, but I think of like a hammer. You can use a hammer to put a hole in a wall if you want, but maybe that's not the best tool if you're trying to cut a hole in your wall. So in my field, it's predominantly SAS and R. I personally use R the most. I use SAS and R about 50-50 probably at work. The reason is because SAS has been validated. The argument, I'll leave that up to the listeners to decide whether that's adequate assumption or not, is that SAS has been validated and R hasn't. So R is more like a living, each package is a living, breathing thing that can change over time. So you can get different results from one version to the next. I predominantly use R because of the flexibility of it. So there's like the graphs that you can make. For me, it was great learning about different packages, some of the vignettes. It depends on who the author, the maintainer is. But two like great examples would be Malcolm Barrett and Noah Griefer. Their documentation is fantastic for the R packages, and I've learned a lot from those. And also for data manipulation. So I used SAS for my master's, and there was 1/5 of the patients I'm dealing with now and had a struggle to reformat it. It's not to say you can't do it. It's just the right tool for the job. So I predominantly use it. I don't know, do you use predominantly Python? Is there one that you do use more than others?
I
Or
mean, we are kind of like a different breed. I mean, we are a bunch of statisticians, so we use predominantly R. I mean, the
yeah,
reason that we use R predominantly is because it's like, we are like a kid in walking into a candy store. So many excellent libraries out there. You don't have to
hmm
write things, from scratch. But yeah, Python is great for, general purpose programming, putting things
yeah,
into production. So what we do is, running all kind of, statistical tests and everything, we use R. But if you want to put it into production, we kind of, change our code, convert it into Python as much as it is possible. I think you talked about SAS. I did learn it, earlier in my career. I remember all that proc statements that you have, there are tons
hmm
of it. I think the argument at that time was, people said that SAS kind of lets you do what you want it to do. Like if you're a statistician, you know your topic really well. You can definitely validate whether it's giving you the output that it should, right?
yeah.
But if you don't know your topic very well, any programming language is,
It
you
still
can
words
use.
it still words from my mouth. Yeah, like to me,
Yeah.
it's all about how comfortable you are with it too. Like for me, my degree's in epidemiology, but I love statistics. So, like I've dove into the math into the math and the code behind how like GLM works in the stats package in R. So there's a lot that you can do with it. But it's the same thing I tell people. If someone wants to use Excel to run an analysis, I hope that you're very comfortable because there's going to be things that you're going to assume doing it. So I think that's also why SAS is used. It gives you a bit of a safety net in terms of that it was correct or assuming that it was correct. Yeah, yeah.
I
Those are the
mean,
two that
talk.
I'm
Yeah.
most. Yeah.
Talking about programming languages, are there any particular libraries in R for causal inference that you would suggest to people?
Yeah, so there's so specifically for causal inference, there's actually a book, I think it's a still work in progress, Causal Inference in R, by Malcolm Barrett, Lucy D'Agostino McGowan, and Travis Gerke or Girk. Um, and there's some good packages there. GG
Mhm.
is one by Malcolm Barrett. Um, Wait It by Noah Griefer. Cobalt by Noah Griefer. And then there's like I'm sure people are familiar with it, but there's a host of packages that are tied in together, tidyverse. So for what I do specifically, to get the data to a point that you can analyze it, there's a lot of data cleaning and data manipulation. So those tools are great, like dplyr, tidier, the stats package. So those are the ones that I mostly use.
Last question, what are the popular resources that you would suggest to, anybody looking to get started with causal inference? I know you already talked about the book from, Hernan, the What If. What additional books or resources would you
Yeah.
suggest?
Yeah, so there's a few. I would suggest that's where I started. And also with that resource, there's R code that accompanies it. So I learn best from reading about it and then trying to do it. A couple other popular resources would be a couple people to follow on LinkedIn, such as yourself, Justin Belair. Adrian posts mostly about RCTs, but there's still a ton of useful stuff that can be used for causal inference. There's the Causal Inference Mixtape by Scott Cunningham that's freely available online. Causal Inference for the Brave and True. I haven't read that, but
Yeah.
I've heard a lot of
Matthew
good things
Speckwer.
about
Yeah, I
it.
interviewed him.
Yeah,
Yeah.
yeah. So those can be the places that I would start. I personally started with Hernan. and Robin's book. And then there's a few different authors that I tend to follow. So Malcolm Barrett would be one, Lucy D'Agostino, McGowan. And yeah, that's kind of my approach.
Yeah, I think these are a exhaustive list of excellent resources for people to follow.
Oh, yeah. I would
Yeah,
add
go
one
ahead.
more. I would be Peter. Sorry, I had one more. Would be Peter Austin. He
Okay.
does a lot of work with propensity scores. So that's kind of my go-to for propensity scores.
Yeah, I'll make sure to list all of these resources down in the comment section. Ryan, this has been really great. Thanks for your time. I'm pretty sure people not only in epidemiology but other domains as well got a rich insight of various things, causal inference from our podcast today. And thank you for so much for your time. I'm sure we're going to have you back in the future discussing
Right.
on all these topics in much more detail. Thank you very
Be
much.
happy to, and thanks very much for having me. It was a great discussion.
Thank you.